Hi, my name is PJ Laszkowicz, and I'm a creative technologist with over 20 years of software engineering and solution architecture experience with some of the world's most successful technology companies and over 14 years of machine learning and artificial intelligence experience. Today I'll be taking you through a brief overview of how I iterate on proven DevOps methods, practices, and architecture to deliver powerful MLOps infrastructure that can deliver apps, services, and models to various cloud and edge computing targets. The case study I'm going to go throughout this talk is a sustainable agricultural project in Africa and South America which needs to operate in low connectivity regions. It's important to define what we mean by sustainable in these types of projects. We may be talking about the economics of operating the service, the stability of the components over long periods, or the ecological impact. In this case, it's mostly about the ecology and agricultural economics. In order to make agriculture economical and ecological, we need to understand cause and effect over long periods. In this case, it means we're going to need historical meteorological or weather data, market data such as commodity trends, and real-time data from the farms themselves. In order to get data from the farms, we're going to need sensors and a method for those sensors to send data to our service. We then need to be able to crunch that data as well as the data from other external feeds, including the market and meteorological data, to build responsive models that can provide a predictive or anticipatory response for farmers to enable reactive and adaptive agricultural operations depending on the environmental and market changes. So where do we start? Firstly, we can assume we have our code repositories. In my cases, I find modular and atomic repositories work best as they allow focus changes and granular version control for iterative encapsulation of features, which is especially useful if you use feature flags and canary deployments and is useful when separating configuration from code in your deployments. We can also assume we have our sensors and cloud API access. We have a restriction in this project. The farms sometimes operate their own cooperative, which will want to own some of the data captured. So in order to be cost effective, we're going to create a relatively portable set of tools that they can run on their own infrastructure. The first step I often take with my projects is to create the required access controls for both my team and the applications that will be accessing our cloud services. My goal is to restrict any and all human access to any environment and instead drive access to application tokens. But this is at its most painful during the initial setup. This project requires OAuth2, OIDC or OpenIDC Connect, along with JavaScript Web Tokens or JWTs as part of the authentication and authorization layer. We can get that easily from most cloud providers, including AWS with Cognito and Azure and Google Cloud with their respective identity platform offerings. We can of course use other tools, and in this specific case we brought in 3 separate components to provide the auth layer needed, including key, certificate, and secret provisioning and storage. If every component requires authentication, then it makes sense to create a high availability auth cluster with common security services needed throughout the platform. We're operating a clean slate here, so we have no pre-existing delivery mechanism. Therefore, the auth layer and the initial continuous delivery components need to be created manually. My approach is to build a cloud infrastructure bootloader for the project. By bootloader, I mean a program that will provision the initial components needed before the rest of the provisioning can be automated. This is quite easy to do with most cloud development kits or even directly with the cloud provider's APIs. If you wanted, you could use Terraform or some other automation tool, but personally I like to create a simple command line program to do this, and often I use most of the same code across projects. There's some time needed to build such a component, but it provides a lot of reuse, so it's a valid investment as far as I'm concerned. It also allows you to write event-driven infrastructure, which Terraform does not. By event-driven, I mean that I can write the program to perform any checks I want, run some operations asynchronously, and create simple or complex dependency trees to adapt to. The end product is often a resilient cloud environment bootloader that can build and tear down the environment easily, enabling for a stateless and portable tool for the DevOps team to use. In this project, the bootloader will provision the required auth services and will initialize a managed Kubernetes cluster with our continuous delivery or CD component. Note that I said CD and not CI/CD. That's because we need to deliver components before we integrate. CI is to CD what C is to C++. It's often not great to create linear pipelines, and in my project the continuous integration component comes later. In our project we're using Argo CD, which is well suited to provisioning Kubernetes-based infrastructure. From this point onwards, any and all infrastructure will be delivered as part of the Argo CD pipelines, which can provision our initial Kubernetes clusters, and Argo CD will ensure they're kept in the state required across our environments. Argo CD is stateless and configuration driven. We use Customize and Helm to template our applications and provision the containers needed. The authentication for Argo CD operates through our original auth cluster, enabling the beginnings of an holistic single sign-on or SSO throughout our environment. To make this work, we're using Envoy and Linkerd on all of our clusters for the Ambassador and Service Mesh respectively. Every request to the cluster will be checked against our auth service to ensure it's permitted, separating our services from any auth concerns and simplifying authentication and authorization to a single point in our platform. None of my services are written with an understanding of authentication or authorization. They're domain focused on the problems they're solving, trusting that the environment they're deployed in will solve the rest. The goal essentially is to deliver a zero-trust pipeline that can deliver the artifacts needed. Now, to make this easier, we apply Open Policy Agent or OPA to our Envoy deployments, which hooks into the external authorization filter. We can further extend it if needed with a WebAssembly filter on Envoy, and I have done this on this project for some niche features and on other projects, but this is largely unnecessary for most projects. I've started to see rapid growth in WebAssembly on these type of projects, and you'll see later how I've started to apply it to the rest of the pipelines too. Now we have our CD tooling, we can take a look at our CI or continuous integration tools. I opted for Tekton in this case mostly due to the fact that I've used Knative a lot in the past, and Tekton is essentially the build spin-off of Knative. I use Tekton to build and test my images and artifacts. I version control containers and artifacts, but I don't stage them, so a single build is enough. Environments are staged, and going back to an earlier statement, I build each environment with the same tenacity to reduce human access. In most projects, it's the humans that break something. So if you can build a pipeline that is resilient and well tested through automation, then it's less likely to experience breakages or downtime. That's not to say it's perfect, by far it's not, but if you give developers access to your environments, I think you're asking for trouble. I use Argo CD to set up a Tekton cluster and a Harbor environment to store container images. I also use artifact storage for various code builds like Node and Python packages, for example. Using Knative and Argo CD enables me to use cloud events to create reactive infrastructure in a standardized way without having to work through esoteric APIs. It also enables me to extend my pipelines through the same cloud events with custom components if needed, which I didn't in this particular project. So far, we have a fairly standard CI/CD pipeline setup. It's more manual than most projects due to the fact we need to productize it for third parties and had to deal with the unusual constraints. I could use AWS Code Deploy, GitHub Actions, or Azure DevOps, amongst others. The tooling should be selected based on the constraints of the project, and I've used and continue to use all of the above across various other ongoing projects. If you've already used one of the above platforms, then typically it's best practice to use what's available rather than starting cold as I have in this case. What I'm missing with the current setup is tangible security through the pipelines. With Tekton, we can add extra steps in every build to support integrity checks on our images. Notary and Falco are two tools introduced across my pipelines to give me a little more assurance that I'm not going to push an image with a brand new gaping hole into production. I use other tools as well, but mileage depends on resourcing available to put the tools into practice. There's no point putting checks and then not being able to respond to those checks. I would recommend, however, that package audits are in there at the very least, and to ensure that any build that fails basic audit checks should outright fail so that someone has to fix it. It's uncomfortably normal to see production code fail audits and still get shipped. Again, if the pipelines comply to a strict governance model and don't permit developer access, then it makes it much harder for teams to sidestep mandatory checks, and it's better for a product to fail an audit and not to ship than to ship and expose the organization. As I'm a service-driven person, I focus on the API developer gateway next. The approach I take in every project is to treat APIs as products. Even if a service will only be used by an internal team, I ensure it's well documented. The API is a governance model which includes pull requests and version control. It also ensures access to the API documentation is easily available. Personally, I separate API documentation from any code as they're not related in my eyes. I could have two different code bases applying the same API, so which repository should I apply it to? I also often like to pull an API specification and test a project against it as part of a build, and I'd rather just pull the specification and not the code to the entire service. As far as the governance goes, it's more idiomatic to write an API specification as part of an agile sprint, complete with pull requests, merges and retrospectives, than to treat it as a functional code exercise. Knowing we have two types of APIs within this project, I needed tools that could support both REST and GraphQL. I use Redoc to produce static sites that can be deployed on any web server, and I use Backstage as my developer gateway. Again, we're using the same auth cluster here, so we only have one place to manage all access. I deploy my service documentation as part of another CI pipeline, remembering that the service specifications are in their own repositories, and Backstage provides my partners, my team, and any third parties with scoped access to the APIs as necessary. It's entirely pluggable and enables a custom web interface to be built to match the rest of your organization's branding. So now we have a fairly healthy DevOps pipeline from source to production. We can start to look at those extra elements that enable us to deliver machine learning models with the same level of quality as the rest of our code. I've seen a lot of machine learning projects stop developing their DevOps technical capabilities once they have a code build pipeline. Many pipelines are much lesser than their classic code pipeline counterparts. There are plenty of data scientists that, in fact, still run machine learning model builds locally and don't write tests. For those that think this is fine, I'm telling you it's not. Models running locally mean data is being stored locally, which is rarely a good thing. To execute a model locally will take significantly longer than most cloud environments, which means you're just wasting time. And finally, if you're executing it locally, you're probably missing out on some great tools, including the ability to run the same model in parallel with varying hyperparameters, which will enable you to pick the best or most accurate model for the job. This means you can test many variations of the same model at once in the same amount of time and automatically pick the most accurate whilst you're busy working, eating or sleeping. I'll cover how this works in the pipelines in a moment. In my project, I use Kubeflow to manage the machine learning pipelines. This isn't a duplication of the Tecton setup, it fits perfectly in the environment as part of the Tecton pipelines. So we can kick off a build process in Tecton, and then it will run the Kubeflow for us. We execute two different streams from Kubeflow, a data flow and a model flow. The data flow uses Feast for feature extraction, and TensorFlow data validation for data validation. Feast enables us to find and configure features separately for our model code, and to enable scalable hyperparameter tuning, I use Ktyb in the model stream. After both of those tasks are done, the flow converges and we can start training the model with the features and parameters provided. Now, this can be scaled to train the model in multiple variations. It's important that data scientists are outputting useful metrics to measure against, otherwise you're not going to get the most from this setup. And when I talk about using the hyperparameters and scaling up, I mean that you can run multiple in parallel concurrently and then get the results back, where typically if you'd run it locally or if you'd run it on a traditional pipeline, you'd only be running one build at a time. And in data science, that is not very productive. Once a model is built, we run TensorFlow Model Analysis, or TFMA, to verify the quality of the model. You can think of this like an integration test. And finally, the model can be deployed by TensorFlow Serving on Knative. Now, all of these TensorFlow tools actually are part of the TensorFlow Extended toolset, which is all about the ability to deliver enterprise-capable TensorFlow models or other machine learning models. It actually works with non-TensorFlow models as well. The model can then be reached by our services, but it's not running on any edge devices now. So how do we deliver this model to the farms? There are two ways we can achieve this depending on the hardware we're working with. On our more powerful edge devices, we use K3s and can deploy directly to those devices in the same way we deploy to the cloud. We can operate tens of thousands of nodes in a single K3s cluster, so phased rollouts can be managed that way if needed, although this takes some work. We can also use device provisioning and distribution platforms like VMware Pulse Center, Azure IoT Hub, or Pelion, for example, to provision the devices, K3s, and then use Argo CD to deploy the configurations. Now, this tends to be quite heavy, though, as Argo CD doesn't understand IoT rollouts and the regional and low connectivity constraints we have to deal with. In some areas, mobile connectivity is extremely slow and costly, so we need to be sensitive to what we're doing when we're delivering a model, containers and data on an edge device. Again, we're passing that cost on to the farms, and we don't want to be increasing those costs unnecessarily. My other approach in this project is to use a Pelion platform to roll out changes to the edge devices in a phased manner rather than depending on Argo CD and K3S to do it. The build artifacts from the Tecton pipelines can be stored, and then the edge devices will pull the new build artifacts when instructed and when available via Pelion. With well-configured monitoring and logging, it's straightforward to see if a rollout is effective, and edge management services enable rollbacks and retries. To ensure one failure doesn't mean an unusable component, I ensure that version service components support a HTTP version header with a suitable default version if none is specified. This works in much the same way as a canary deployment and ensures older clients can still operate until an upgrade is complete, and then the service can be shut down. It also means that API clients can just default to the latest API if needed without having to understand a specific URL pattern for versioning. Often multiple versions operate at the same time for months, and in some cases years, but this doesn't adversely affect the way that these pipelines operate or the underlying architecture of the project. We simply handle the various version requests within the cluster deployment in Argo CD, which provisions an envoy configuration using the open policy agent again to direct the request to a suitable version of the service or model. So now we have a full MLOps pipeline running. We can start looking at the data. In this project, I built a data platform with a data lake, reporting tools, and included model federation, but that's perhaps going a little bit too far for this talk. In many cases, you'll want to include a data ingest and data storage to be part of the pipeline, as your data scientists will need to access those data sources when training the models. This differs to most DevOps pipelines where data is not required to deliver code and where data is in fact an artifact of a production environment and not a code build dependency. The data pipelines are yet another set of clusters provisioned by Argo CD, and in reality should be one of the first components added to Argo CD for the data scientists to work with. There are a lot of tools available, and a lot of tools I've used to manage data ingests, processing, engineering and storage, but in this specific case I'll simplify it to the most important components used in this project. Firstly, data ingest pipelines need to include streaming data from the edge devices located on the farms and bulk ingest from the third-party commodity and meteorological data hubs. For streaming from edge devices, I used Apache Flink. Although irrelevant to this talk, I would like to point out that I deployed fog computing and aggregate edge nodes to the farms to reduce the amount of data sent by the mobile data connections. This means the fog and edge networks would aggregate their own data, reduce it as needed, compress, and then send the results in a condensed data stream, reducing the data costs and upload times. It also allows us to deploy some models that do additional machine learning on the edge that can reduce further data sending as well, so we can do some of the processing locally and never have to send the data to our actual cloud storage. If you're using AWS, you might want to use Kinesis. If you're using Azure, you could use Event Hubs, among others. Again, there are a great many choices, and the best decision can be different depending on the existing tooling, skills available, finances, and a great number of other potential constraints. Apache Flink operates on its own cluster and is provisioned like every other component with Argo CD. The resulting data is stored in Apache Druid, a time series data solution for analysis. For the third-party data sources, I used Apache Spark, which would pull in the data from external sources via REST APIs, aggregate large amounts of data in memory, and then store the results in Terminus DB or Apache Druid, depending on the type of data we're dealing with. The code for other data ingests is written in Python and is built, tested, and deployed with Tecton and Knative. We're aiming for consistency to reduce the likelihood for new skills to be needed and anomalies to be encountered when provisioning tools and services. These new ingests are great for gathering the data, but the data is almost always unsuitable for training the models with, so we need another step. Our training data will come from a data warehouse specifically allocated for model training. It uses columnar data storage in the form of Parquet files and is provisioned by, yes, you've guessed it, Argo CD. In this case, we're provisioning storage and attaching it to a Kubernetes cluster. Storage varies on the provider, but we could be looking at S3 or Data Lake Gen 2 storage, depending on if you're using AWS or Azure, and there's various other options as well. All we really care about at this point is the fact that we have raw file storage and that we're going to be attaching it to our build pipelines. The training pipelines then include a step to ingest the data and prepare it for training. And again, we're typically working with Python code, so it's not complex to manage. Data for training and validation and production data may not be the same, but often you will want to improve your models repeatedly over time as new data arrives. So it makes sense to have some form of sanitized production data feeding into your model training pipelines, even if there's some additional engineering step in between. So the important thing to remember is that, one, models are more alive than programs. They change over time as data changes, regardless of whether any code is modified. So rebuilding or retraining and redeploying should be a regular occurrence. This takes unique considerations compared to other types of code pipelines. And two, as almost all data is sensitive in one form or another, it is vital you build pipelines that are secure, which means they don't allow developers in. Pipelines aren't for debugging, so there's no reason to let your guard down, and debugging doesn't require production data unless you're doing something very wrong. And finally, I mentioned we go back to WebAssembly at some point. Although not related to machine learning, there's been an increasing amount of work in the projects I've done in replacing some of the Knative processors with Crustlet for processing data. This means reducing serverless from container images to compiled WebAssembly programs, which obviously reduces the amount of memory and CPU usage as well. I expect in the next 18 months, a lot of what would have been traditional container builds for me will become atomic and minimal WebAssembly programs written in any language of my choice, and this feels like a significant modernization for cloud infrastructure. WebAssembly is already finding an increasing presence on the edge devices I deploy. It's used in my Envoy deployments for extending the filters, including in Istio and Ambassador, and it's landing in more and more web projects, so serverless WebAssembly feels quite right. I hope you enjoy this talk, and feel free to reach out if you'd like to know anything specific, either about how I build DevOps and MLOps pipelines or the specifics of data platforms I build for machine learning projects, and thank you for your time.